and welcome to a video for shear and moment diagrams. You'll notice that the shear and moment diagram we're going to be talking about in this particular video does not have any numbers associated with it. It is simply variables, and we'll use this to describe the basic procedures for drawing correct shear and moment diagrams. See, here we have a basic procedure outlined, and the first step is to draw a free body diagram, and we will use that free body diagram to solve for reactions. So in this particular step, you will apply what you already know about static equilibrium. In this case, those reactions are simply represented by R1 and R2. The next step in drawing complete and proper shear and moment diagrams is to set up the axes for the shear and moment diagrams. We'll do that by simply drawing vertical lines from the ends of the beam down to the bottom of our paper. Now, drawings in engineering, the bigger the better is a good rule to follow. So if you are using a typical piece of graph paper, make use of that graph paper to give yourself space to draw large shear and moment diagrams. We always want to start with the load conditions, followed immediately by the shear, and finally followed up by the moment. That is the order in which to draw your shear and moment diagrams, and we'll understand that better as we apply our load, shear, and moment relationships and begin to work through these diagrams. It should become clear. The next step along our basic procedure is to divide it up into intervals, looking at the abrupt load changes. So in this case, we notice that the load it changes, but not abruptly from A to B, and then suddenly at B, things change. So we'll just draw a line down, and that will let us know that at that point, something might be happening. Same thing we see here where this moment is applied. And so we'll again just extend a line from there. Okay, now we come across at D, and we have a load applied at D. Pardon that quick interruption there, technology makes things fun. Now we come over to point E, we've got another abrupt load change, so we'll just extend that line on down as well, and then we're at the end of the beam. Now it's time to begin working on our shear and moment diagram, and you always want to work left to right. We'll create the shear diagram first, and then we'll come to the moment diagram. We're going to use load, shear, and moment relationships, and we'll write those up here in this space as we need them. The first thing that we encounter at point A is this distributed load, and it's a ramp load, therefore it's a triangle. And what we're going to need to find about this triangle is its area. Just using the area of a triangle, we'll call that A sub 1. Why do we need to know that? Well, we need to know that for a couple of reasons. The first reason is the change in shear between 2 points is equal to the area under the load curve. Or in mathematical terms, that's the integral. So we know that the change in shear from point A to point B is equal to the area under that particular load curve. We know that the shear must always start at 0. And we'll see in a bit that it also must end at 0. If we're starting at 0, and this relationship tells us that the change in shear between 2 points is equal to this area, we know that the shear value at point B is area 1, or the area under that triangular load. Now, is it positive or negative? This brings us to one of our hints. The shear diagram moves in the direction that the load is pointing. So in this case, the load is pointing down, so our shear diagram must be reducing to a value of A sub 1. Now, how do we figure out how to connect those two dots? We use one of our other load, shear, and moment relationships, this one being the slope of the shear diagram is equal to the magnitude of the load curve mathematically the slope of a function being described as the first derivative. And we see that the slope of the shear curve equals the magnitude of the load curve. At A, the load is equal to 0, so there is no slope, so we could draw a line there. At B, the slope is something other than 0, pointing down, so it is negative. The only way to connect those two is with a parabolic function, or a curved line. Now we know it's parabolic, and we're going to label that as P, because if we have a linear load, we will have a parabolic shear. So since this is linear, that is parabolic. And that goes back to this relationship here. All right, we're moving right along. The next thing we encounter is this applied load at the reaction at point B. Now, an applied load, whether it's a reaction or an externally applied load, again following this hint that the shear moves in the direction of that load, we will just jump up a magnitude of R1. So at this point, we would be at the value A1, and in fact, this is actually a negative value, plus the magnitude of that reaction, R1. And then that is connected with just a vertical jump. Continuing along, in this particular region, there is no load. Therefore, there is no slope, or the slope is 0. If W equals 0, the slope of the shear diagram is then equal to 0. There's also no load, so there is no area under the load curve, so there is no change in shear between 2 points. And we can say that this line marches right along until we encounter this moment. Now, a moment does not affect the shear curve. We'll see in just a moment that it absolutely affects the moment diagram, but for now we can ignore that moment and continue to plot along with 0 slope until we encounter this load P, having the opposite effect on our shear curve than this reaction is having. It bumps it down. So we're now at a value of negative A1 plus R1 minus that applied load P. Now again, in this particular region, there is no load, therefore there is no slope, and there is no change in shear between 2 points, so our shear curve continues to march along until we encounter this distributed load. Now we must find the area, and we'll call this area 2, and that's just a rectangle, or we could say that's W2 times L5, this length 5, and if we wanted to be complete over here for this area, we could say that's 1/2 of W1 times that length L1, just the area of a triangle. The bottom line is we wanted to find that area, because it's that area that tells us about the change in shear between 2 points. Now again, that is pointing down, so that's going to be a negative change. Since our slope of the shear curve is equal to the magnitude of the load curve, if we have a constant load, what's it going to be? A linear shear curve. Absolutely. So since we have constant load, we have linear, and we'll note that with an S for a linear line. We know that from this shear and moment relationship, load shear and moment relationship. Well, now we can see that we're at some value of negative A1 plus that reaction 1 minus P minus that area 2. And I said at the beginning that we were at 0, or we should close at 0. How can we ensure that happens? We add the reaction at 2, and mathematically that should result in 0, positive jump. And what is this? That is really nothing more than the summation of forces in the y direction is equal to 0. So equilibrium comes back and helps us out once again. Talk about that just a little bit more. This term right here, this area 2, what is that really? That is an externally equivalent concentrated load, which you would have used when calculating the reactions, which, if you recall, was that critical first step in our basic procedure. Just wanted to highlight this value here, 0. The shear diagram must close. And by close, we mean it goes back to 0. That's our shear diagram. The next step is then to use our shear diagram to create our moment diagram. And in order to do that, we have similar relationships relating shear to moment from what we used relating load to shear. One of those relationships is that the change in moment between 2 points is equal to the area under the shear curve between those 2 points, and similarly, the slope of the moment diagram is equal to the magnitude of the shear curve. Those are the two key relationships that we will use when building the moment diagram. Now, once again, the moment diagram, just like the shear diagram, must begin at 0, and we're going to need to calculate a lot of different areas. We need the area of all of these various shapes on our shear curve. So one thing that I typically do when I'm working on my shear and moment diagrams is, before I even dive into my moment diagram, I'll just calculate all of these areas. So we'll just call this area 3, area 4, area 5, area 6. Since this piece here is a composite shape, we'll break that up into actually 2 areas, a triangular section and a rectangular section. This piece here may be a shape unfamiliar to some of you. If you look on your RDC, your reference data card for CE300, that's a parabolic spandrel. Alright, now making use of these areas, we notice that this is a negative area because it is below the axis of our shear diagram, and so we know that the change in moment between 2 points is the area under that curve, so we go from 0 to some value, which will be the magnitude of that A3. Now, how are these two dots connected? Applying a similar logic that we applied when comparing our shear to the load, making use of the relationship that the slope of the moment diagram is equal to the magnitude of the shear curve, we start with a magnitude of the slope of 0, and it increases negatively. The only way to do that is through some curved function. Since this is parabolic, we have a parabolic shear curve. Therefore, we must have a cubic moment curve. Since that is parabolic, this must be cubic. And we'll label that with a C, with a circle around it. Continuing along with the similar logic, we know that our moment will now change the magnitude of this area, and that is a positive area. So we will have a positive change. Since we have a constant shear, we have a linear moment curve. Since that is constant, this is linear. And we'll denote that with an S with a circle around it. And we know that this magnitude is, this is a negative value for A3 plus A4. And I'm just going to call that the moment at point C. Now, at point C, we encounter that moment. We said that the moment does not affect the shear curve, but it absolutely affects the moment curve. Keep this hint in mind. A clockwise moment causes a positive jump. In the moment diagram. With that hint in mind, this we can see as a counterclockwise moment, therefore it must be creating a negative jump. So this is a negative jump, and that would be the moment at point C minus the applied moment in. Now we come back to a nice constant shear. So we again have a linear slope, and this gets us to the moment value at D. Again, just continuing on with our addition and subtraction routine. Now we have a negative moment, or negative area, so a negative change in moment, which would get us to the moment at E. And finally, we see the last portion of this area, and we notice that the slope is increasing negatively. What does that mean to the shape of our diagram? The only way for the slope to increase from this to this would be to have a concave down. This curve is not working out quite well, but it is a concave down shape. Since we have a linear shear, we must have a parabolic moment curve. And we will label that with the P. Now, how do we make sure that we ended up back at 0? We add all this stuff together. And in reality, what we're going to do is add up all of these areas under the shear curve, and also include any applied moments. And that will all add up to 0. It is absolutely critical that the moment diagram closes. And you'll see that that is one of the steps on our basic procedure, that your shear and moment diagrams both close. And now, before you say I'm done, I'm moving on to the next problem, you want to make sure you check for completeness. Is everything labeled? Well, let's check that. We've got this curve labeled as a P. We have not labeled this line up here. That is a straight line segment. This is a straight line segment, and that is a straight line segment. We also want to make sure we have all of our values labeled. So we make sure that all of our key points values are clearly labeled for the reader, the user of these shear and moment diagrams, to clearly understand what's being communicated. Checking the same thing on our moment diagram, we've got our labels. We missed one here. This is a straight line segment, since that is a constant value of shear. We have a linear segment of our moment diagram. And again, we'd want to make sure that all of our key values are clearly labeled with their magnitudes. That will generate complete shear and moment diagrams. We'll talk about in beam design what we use these shear and moment diagrams for, but really the bottom line is so that we can find the maximum shear anywhere along the length of the beam and the maximum moment anywhere along the length of the beam. That is the real purpose of our shear and moment diagrams. An absolutely critical skill. We recommend that you practice shear and moment diagrams many times to develop the skill. Follow the basic procedures, understand these load, shear, and moment relationships. These are found on your reference data card. They are also found on page 115 of your study guide. That is for term 08-1. Also, you'll want to take a look at page 450 of your textbook for another explanation of this procedure of calculating shear and moment diagrams.